Hi, I'm Kathy Stark. In this lesson, we define sequences in series. We look at summation notation and some properties of that, and we support most of our work with the TI-83 graphing calculator. Let's begin with the definition of a sequence. A sequence is a function that has a set of natural numbers as its domain. Let me show you with an example. What we're going to do with this is just write the first 5 terms of the sequence. A sub n, that's a subscript, equals 1/3 to the n power times n minus 1. When we're done, we'll support our answer with a graphing calculator. The first term of the sequence occurs at the n value 1. What I do is substitute 1 into the formula to get 1/3 to the first times 1 minus 1. Now 1 minus 1 is 0, so the first term of this sequence is 0. To get a sub 2, substitute 2 for n in the formula, 1/3 squared times 2 minus 1. 1/3 squared is 1/9 times 1 is 1/9. The third term of the sequence is found by putting 3 for n. 1/3 to the third times 3 minus 1. 1/3 to the third is 1/27 times 2 is 2/27. To get the fourth term, I'll put 4 for n. 1/3 to the fourth times 4 minus 1. Now 1/3 to the fourth is 1/81, 1/3 to the fourth. 4 minus 1 is 3. 3/81 reduces to 1/27. To get the fifth term of the sequence, I need 1/3 to the fifth power times 5 minus 1. Well, let's see. 1/3 to the fifth power is 1/243, and 5 minus 1 is 4. This is the fraction 4/243. The way that we write down terms of a sequence is we list them separated by commas. I'll do that here. First term 0, second term 1/9, then 2/27, then 1/27, then 4/243, and so on. The sequence continues. Well, we can get a TI-83 to show us those terms. Here's what we're going to do. First of all, we turn on the calculator and find your list option behind stat. If you choose list and go to operations, you can see option 5 says sequence. Sequence requires a few arguments. The first thing we put in is the formula. I'm going to put in then parentheses 1 divided by 3, and I like to use the x. I need to raise it to the x power. I like to use the x variable key. Now next to that is the rest of the sequence, which was n minus 1, but I'm using the variable x. In sequence now we need a comma and the name of the variable, then a comma and the number of the first term, comma the number of the last term that you're interested in our case 5. So I want to go from the first through the fifth term. Close the parentheses for sequence and push enter. And what happens is the sequence is listed. Now, I intended to make these fractions, so let's look at math and choose fraction. And what it will do is take our sequence, if I push enter, and change the terms to fractions. And you can see that these are exactly the things we found by hand. There's 2 specific types of sequences I want to define. Finite sequences have a finite set as their domain. Notice that this finishes with n. Infinite sequences have the whole set of natural numbers as their domain. This is a non-ending set. Let's look at an example. What we want to do here is determine whether the given sequence is finite or infinite. We're told that the first term is 3, and for n greater than or equal to 2, less than or equal to 10, we find any term beyond the first term with this formula. A sub n is 3 times a sub n minus 1. Each term is 3 times the preceding term. Well, let's start listing out some terms to determine whether this is finite or infinite. I know the first term. The first number I should choose for n is 2. And using this formula, I see that a sub 2 is 3 times a sub 2 minus 1, which is 3 times a sub 1, which is 3 times 3. Remember, a sub 1 was given, which is 9. The next term, a sub 3, again using this formula, a sub 3 is 3 times a sub 3 minus 1, which is 3 times a sub 2, which is 3 times the 9 I just found, or 27. If I continue, a sub 4 is 3 times a sub 4 minus 1. That's 3 times a sub 3, which is 3 times 27, or 81. Now I could write out all the terms, but I know that the last value I'm allowed to choose is 10. That's going to make this a finite sequence. It's not necessary to write out every term to determine if a sequence is finite or infinite. We're going to move on from sequences to the idea of series. A finite series is an expression of the form S sub n is a1 plus a2 and so on up to an, and it's written with this notation. This is called a sigma or summation symbol. I equals 1 to n gives us something called the index, and inside is the particular term that is being summed here. This is a finite series. It finishes. An infinite series looks very similar, but notice that it continues on, and that the upper index of summation is infinity. The letter I again is called the index of summation. Let me show you how that works. Here's what we want to do. Evaluate the series, and we're given the summation as j goes from 1 to 4 of 1 over j. Evaluate means actually find the sum. For this particular example, I'm going to write out the terms and then add them together. The first term in the series occurs at the first value of the index, 1. Substituting that into the formula for the series, I get 1 over 1. Now go to the next value of the index, and the index increases by 1. So the next value is 2. The next value of the index is 3. Putting that in, I get 1 over 3. And the last value in this particular series occurs at 4, the upper index. All I need to do is add these together. I need a common denominator, that is 12. 1 is 12 over 12. 1/2 is 6 over 12. 1/3 is 4 over 12. 1/4 is 3 over 12. 12 and 6 is 18, and 4 is 22, and 3 is 25 over 12. It's also possible to use a TI-83 calculator to do this kind of a problem. And let me show you how we might do that. We need to do this in 2 steps. I'm going to begin with a clear screen. The first thing we're going to do is enter our sequence as we did previously, and then store it as a list. Our sequence this time has the term 1 divided by a variable. Again, I like to use x. Next to that, I put, after a comma, the variable, and then after a comma, I'm using terms 1 through comma 4. Now, instead of entering and listing the terms, I want to store this. That's down the left column, second button from the bottom on the keypad. I want to store it as a list. The list names are also on the keypad in yellow. I'm going to choose second L1 and push enter. What happens is this sequence is stored as list 1. Now I'm going to sum list 1. Again, go to list. At this time, to math. And option 5 is sum. Inside the sum, put L1 by selecting it off the keypad. Second L1. Closing the parentheses, I want my answer to be a fraction so I can see if it's 25/12. So I'm going to push Math and select the arrow to a fraction option. And the answer is 25/12. That supports our analytic work. Well, it's your turn to try a problem. Here's what I want you to do. I'd like you to evaluate the series, and we have the sum as I goes from 1 to 5 of 2i plus 1. Stop the tape while you work and restart it when you're ready to check. Let's see how you did. I'm going to evaluate it by hand using first of all 1 for I get 2 times 1 plus 1. Then 2 times 2 plus 1. Then 3, 2 times 3 plus 1. Then 4, 2 times 4 plus 1. And then 5, 2 times 5 plus 1. Stop at the upper index. These numbers are 3 plus 5 plus 7 plus 9 plus 11. Adding them together, that's 8 and 7 is 15, and 9 is 24, and 11 is 35. Let's support that with the calculator as we did previously. We want to go into List, Options, Sequence. We're going to put in 5x, not 5x, excuse me, 2x. 2x plus 1, comma, x, the variable, comma 1, comma 5, and we want to store it, and I'll store it as list 1 again. And now we're going to sum, so second list, Math, option 5, and second list 1, and the answer is 35. That supports our work. Now, series have certain properties as follows. Suppose that these A's and B's are two sequences and C is a constant. Then the following properties hold for every positive integer n. Let me see if I can explain them. The first says, if I sum from 1 to n the constant C, I end up with the number n times the constant C. The second says, if I sum from 1 to n the constant C times a sub I, that's the same as the constant C times the sum of a sub I. The third says, if I sum from 1 to n ai plus bi, that's the same as summing each individually and then adding. The same is true of subtraction. If I sum the difference, that's the same as the sum of the first minus the second, the sum of the second sequence. There's also two summation rules that you need to know and be able to use. The first says, if I sum I squared, that's the same as 1 squared plus 2 squared and so on. And that sum will always be n times n plus 1 times 2n plus 1 over 6. Notice that the n in the formula is the upper index. If I sum I, that's 1 plus 2 and so on, that sum will always be n times n plus 1 over 2. Again, notice that n is the upper index of summation. Let's use all of these together to do the following. So we're going to use summation properties and rules to evaluate this particular series. What we're given is the sum from 1 to 5 of 4i squared minus 2i plus 6. And then we'll check our work, support our work with a graphing calculator. I'm going to begin using a few of the properties, beginning with separating this into 3 pieces as follows. It's the sum I goes from 1 to 5 of 4i squared minus the sum I goes from 1 to 5 of 2i plus the sum I from 1 to 5 of 6. Now in the first sum I can pull out the constant using a property. For sum I goes from 1 to 5 of I squared minus 2 sum I goes from 1 to 5 of I, and I'll hold this for just a moment. Now I had a summation rule that said if I summed I squared, what I could do is take the upper index as follows. I can take 5 Let's look back at the rule so you know what I'm doing. The rule says if you sum I squared, take n times n plus 1 times 2n plus 1 over 6. So in this case, 5 times 5 plus 1 times 5 times 2 plus 1, all of that over 6, minus 2. Now we need to sum I. Let's look back at that rule so we can use it. That rule says take the index times the index plus 1 and put it over 2. In this case, that is 5 times 5 plus 1, all of that over 2. The last thing I'm going to use is a summation property. I'm only summing a constant here. I can take that, this should be a plus sign. I'm going to take that constant times the index. Let's do one simplification step and then use a calculator to help. What we want to write down is 4 times 5 times 6 times 11 over 6 minus 2 times 5 times 6 over 2 plus 30. Now using a calculator to simplify, this comes out to 220. Let's support this problem by using a graphing calculator. On our calculator, we want to go into list and operations, and we're going to do, actually I want to go to math because I'm going to do everything at once here. I'm going to begin with sum, and in my sum now, by choosing list and operations, I'm going to put a sequence. So I'm going to find a sum of a sequence all at once. The sequence is 4x squared minus 2x plus 6 instead of I, then comma the name of the variable x, and then comma 1 lower index, comma 5 upper index. Now I'll close parentheses for the sequence and then close for the sum and push enter, and I get 220. What I want you to do is the following. Use summation properties and rules to evaluate this and support your answer with the graphing calculator. Let's see how you did. The first thing we're going to do is separate this into two pieces. The sum of 5i from 1 to 5, the sum of 3 from 1 to 5. This is 5 times the sum of I, which takes the index times the index plus 1 over 2. And the last term is going to be 3 times the upper index. Simplifying that, the result is 90. Let's again use a calculator. As we did before, we'll choose second list math sum, second list operations sequence. Put in the sequence as 5x plus 3, comma x, comma 1, comma 5, close, close, enter, and we get 90. In this section, we looked at sequences in series and some properties of summation notation and rules. Practice by doing some of the problems in your textbook.